Okay, it may have caused a little confusion in that prior video because whenever we calculated the pooled variance, I had actually calculated the pool standard deviation. Recall I had taken the square root of this, but in the lecture notes, I just fixed this to leave it as the variance, so I didn't take the square root. So instead of getting a value of 2.06, we have 4.24. And so all of these formulas now follow directly from up above. So if I cause any confusion, the notes now, in this example, they follow directly from our formulas up above. So SP squared here, I now leave it as 4.24. So sorry if I confused anyone there, but it's just a small change. Okay, so now we're moving on to paired differences and means. So in this case, paired differences. So these samples are not independent. In fact, they are what we call dependent. And so what we're going to say is assumption one is violated. So recall assumption one was that we were sampling from two independent populations. But now instead of taking two samples and comparing the means, we're going to sample from, say, one population. And we're going to do that twice and then compare the means from our two samples from that same population. So we're going to call this repeated measures. We can think of this as like a before-after program. Say for a weight loss program, we take everyone's weight at the beginning of a program, and then we take it at the end of the program, and then we see if they lost weight. So let's visualize this. So we take one sample, and we obtain a sample average. We'll call it X bar start. So X bar start. And then time passes, and then we, from the same group of people or subjects, whatever, we take another sample and we calculate their end average, so X bar end. So we might think of this as this is the weight at the start of the program compared to the weight at the end of the program. So it's not two different groups. It's the same group being measured twice. And we're going to call that repeated measures. So what we're interested in testing is our hypothesized difference is going to be mu start minus mu end. We're looking at the difference over time. So we'll estimate this by d bar, which is x bar start minus x bar end, and that is just the sum of all of the individual paired differences divided by n. So d1, d2, dn, those are just the individual differences. So that would be for, say, subject 1. So let's take me, for example. If I'm D1, that would just be my ending weight minus, or my starting weight minus my end weight. That would be D1. And then D bar is just the sum of everyone's difference. So it's the average difference over time. But another way we could do this is we just take measurements in one sample and pair them with another sample. And we're going to call that matched pairs. So I think the easiest way to visualize this is to just look at an example. So comparing prices of goods between, say, Costco and Walmart. So here, what we're doing is we're pairing up the price from Costco and Walmart for individual items. So we're checking the price of chicken broth at Costco and Walmart, and then we're going to take the difference in price. So 1.92 minus 1.89 is 3 cents. And then we're going to look at another product. So we're pairing up vanilla ice cream from Costco and Walmart, take their difference in price, and you get 0.0 or 0.68. So this would be the same procedure as that weight loss example. It just looks a little different. One, we're sampling the same group twice over time. Here, we're just pairing up subjects. We're pairing up their samples. So one's from Costco, one's from Walmart, and we're pairing by the product. So in all of these examples, these are not independent, but dependent. Right? It makes sense because if you're measuring my weight before and after a program, those aren't independent samples, right? They're dependent on what I do in that time. Same with these, like the chicken broth price is not independent between Costco and Walmart. We would expect there to be similarities. So those aren't independent pricings. So here we would be, in this example, we're taking the difference. We're doing the average from Costco minus the average from Walmart. And again, we estimate this the same way. D bar is just the average difference, or just the sum of the averages, or sum of the differences divided by the number of differences. So same thing, D1 to Dn are just the sample of differences, and D bar is the average difference. Okay, so doing this, we need to consider our confidence intervals. So it's going to be our average difference plus or minus t. So it's just going to be n minus 1 degrees of freedom, alpha over 2. So it's just the standard deviation divided by the square root of n. So the standard deviation here is just like our most basic formula for standard deviation, like what we learned way back in chapter 3. It's just we're taking the standard deviation of the differences. So d1 to dn. And then our test statistic is just t-stat is equal to d bar over sd over square root of n. Okay, so let's go ahead and do an example. So we're doing this weight loss example. So we took everyone's starting BMI and then ending BMI. And we already have this would be d bar, so the average of the differences, and we were already provided the standard deviations. So we want to see, so can we conclude that the average BMI was lower at the end of camp compared to the start of camp at the alpha equal 0.01 level of significance? Okay, so we need to recognize that this is a paired differences because we're measuring the same people twice. We're doing their starting and their ending BMI and taking the difference. Okay, so we have X bar start is equal to 34.9, X bar end is equal to 31.6. And then D bar is 34.9 minus 31.6, which is 3.3. So standard deviation of start was 6.9, standard deviation of end was 1.5, and then SD was 1.5. Okay, so when we think about our assumptions, we recognize that this is a dependent sample. So we are going to do a paired test. Okay, so let's start with our hypotheses. So null and alternative. So we think that people are going to drop BMI across camp. So when we think about mu D, the average difference, so we'll define it as mu start minus mu end. So if we think they're going to lose weight, then that means start would be bigger than end, and this difference would be bigger than 0. So this is, let's think about this as mu start bigger than mu end. And this is one-sided. So we're not just looking for a difference, we're actually testing specifically to people lose BMI. So mu D here is mu start minus mu end is less than or equal to 0. Okay, so t-stat will be equal to d bar square root n over sd. So we already have these values. So D bar was 3.3 and SD was 1.5. What's our sample size here? N here is 76. So let me rewrite that. We have N is 76, alpha is 0.01. So t-stat, D bar is 3.3 times the square root of N, which is 76, divided by SD, which is 1.5, and we get a value of 19.18. So let's do our rejection region. This is one-sided, greater than, and so because our alternative hypothesis is greater than, that means our rejection region will be greater than a positive. So we will have T stat bigger than T 75.01, right? N minus 1 degrees of freedom. So this would be T stat bigger than, so if we look this up in our table, 2.3771, or of course using Excel. So now our conclusion, we just plug t-stat into rejection region. So we have t-stat is equal to 19.18, which is bigger than 2.3771, and this is T 75.01. So this is in fact true, and so we will reject H naught and accept HA. Right, 19.18 is indeed bigger than 2.3, therefore t-stat is in the rejection region, and so we reject the null hypothesis. So now we need to provide our interpretation, which is there is enough evidence to conclude that the mean BMI was lower at the end of camp compared to the start of camp. At the alpha equals 0.01 level of significance. Okay, and then let's go ahead and do a confidence interval to practice. So let's do a 98% confidence interval. So this is D bar plus or minus T, so 75, and then alpha over 1, so 0.01. So I'm using, here alpha is 0.02 because we're doing a 98% confidence interval, times the standard deviation over square root of N. So we just plug in, we had 3.3 for D bar, plus or minus, we had 2.3771 for our t value, standard deviation 1.5, divided by the square root of 76. And we get 3.3 plus or minus 0.409, which is 2.891 to 3.709. So we're 98% confident that the average change in BMI, or the BMI decreased somewhere between 2.8 and 3.7.